Well, hello, Geography 212. This is going to be your last lecture. Appropriately enough, we're going to talk about climate change. Okay, I'm sure we've heard a lot about this. I want to start this off by talking about, historically, the geologic time scale. Now, if you're not familiar with this geologic time scale, the way it works is it's going to start right down here at the bottom. It says 4,600. That's actually 4.6 billion years ago when we believe Earth was formed. All right, so 4.6 billion years ago when Earth was formed. We can go on up and see all these divisions here. Okay, see Cambrian, Ordovician, Silurian, so on and so forth. But if you look over here where we have eras, you can see we have Cenozoic, Mesozoic, and Paleozoic. The divisions between the Paleozoic and the Mesozoic and Cenozoic are there because there was massive extinction of species right at those times. Historically, geologists have thought that, what's the reason for these mass extinctions? Mass extinction, climate change, warming, cooling, it's not really known. Until we get up here now between the Mesozoic and Cenozoic, we know now that there's very strong evidence for an asteroid impact at the tip of the Yucatan Peninsula, and that crater is about 200 miles in diameter. So for an asteroid impact to create that size of a crater would have created an incredible explosion, hurtling tons and tons of material into the atmosphere, aerosols, bits of rock. And that would have probably been in the troposphere, maybe even in the stratosphere for years. That would have effectively reflected shortwave solar radiation, killing off plants because photosynthesis would not have been possible. If you kill off the plants, you're going to kill off a lot of the animals that eat those plants. In this case, it was the dinosaurs. Then if we move on up here to the Pleistocene, and we're currently in the Holocene, the Pleistocene was an event where we had at least 4 major glaciations in both North America and Europe. And then 10,000 years ago, the Ice Age ends. Why? Climate warmed. The point I want to make here is that historically, throughout Earth's history, there have been tremendous swings of climate change. It's gone on naturally, okay? So climate change is nothing new to this planet, okay? And had nothing to do with human intervention, at least prior to the age of industrialization. So I just really want to start off by saying that. All right, let's take a look at some of the causes of climate change historically on the planet. You can see we'll take a look, number one, at what was initially called continental drift. We now call it plate tectonics. Volcanism, these are volcanic eruptions, what effect they have had. Number 3, does the sun vary in intensity? Number 4, we'll talk about the Milankovitch cycles. And finally, number 5, we'll talk about human activity. All right, for those of you not familiar with this, the idea of continental drift, that's how it started off. That's what we called it back in the 1950s and 60s. It really wasn't proven until about 1970. So this is a recent theory that has been proven. And if we start here about 250 million years ago, we can see that all the continents were together as one landmass. It's called Pangea, which just means one landmass. And then you can see they started drifting apart. We go down, through these different divisions here. Now, how does this affect climate change? Well, I'll give you one example. If we take a look at the present day configuration of the continents, here's North America, Europe over here. Look at the Atlantic Ocean. Look how wide it is here. Well, we know today there's an extremely warm current that runs up from the Caribbean, up the east coast of North America, and feeds very warm water into Scandinavia, Europe, Western Europe, places like that, and keeps that climate very much warmer than it would be if that warm ocean current wasn't there. Well, look, just go back to the Cretaceous 66 million years ago. Essentially no Atlantic Ocean. So that climate was much colder back then in Europe, up in this area here. So just the fact that these continents move around, in one example, allowing very warm water to penetrate high into the Arctic, that's had significant climate change into that area there. And there's just many examples of that, but that's one that affects us here and one that affects Europe. So the continents moving around has always changed the climate around the world. Okay, what about volcanic activity? All right. Well, yeah. Okay. If we take a look at, this is the one example on the graphic there I've given you is the eruption of Mount Pinatubo back in 1991. Mount Pinatubo was over in Indonesia, and it was a very large eruption. It was actually called an ultraplinian eruption. That's about as big as they get for conventional volcanoes. And look at the graphic there. You can see worldwide temperature change. It significantly dropped for almost 2 years after this volcano erupted. Now, why is that? It's because the sulfur dioxide that put out into the atmosphere, these are aerosols, these are solid bits of sulfur. They were able to reflect shortwave solar radiation, not allowing as much shortwave solar radiation to reach Earth's surface, and therefore cooling us down. Okay, so we've seen this in our own, recent history. 1991 wasn't that long ago. Okay, and there have been others in the past. Matter of fact, there have been larger volcanic eruptions in this. Back in the I think it was 1812, around there, Mount Tambora went off with significantly cooling the planet back then. So anyway, we know the volcanic eruptions can change the climate. Probably for rather short periods of time, but nevertheless can change the climate. Speaking of Mount Pinatubo, look at the effect just here in the United States. This map is showing you June, July, and August of the upper Midwest in the U.S. You can see places like Michigan and Wisconsin were cooled off by as much as 6 degrees during the summer. Okay, so it was a significant cooling event that Mount Pinatubo caused. All right, so we've got clear evidence of this. All right, what about solar variability? In other words, does the sun put out the same amount of shortwave solar radiation all the time or not? Because if it's not, it could definitely warm us up or cool us down. We have something called the solar constant. This is the amount of shortwave solar radiation that reaches Earth's surface. But we measure it up at the top of the atmosphere, and we measure it in units of watts per meter squared. And we call it the solar constant because it does not vary. And it's 1,366 watts per meter squared. We haven't seen variability in that over recent history. However, if we do go back into the 1600s and into the 1700s, you'll see something here called the Maunder minimum. What that's taking a look at is there was very few sunspots, a minimum of sunspots. Maunder was the guy that was observing this. Now, sunspots, what they are shadows of flares. So in other words, the more sunspots there are, the more shortwave solar radiation the sun's putting out. So if we see a minimum number of them, we might be able to interpret that as meaning less shortwave solar radiation coming out. Therefore, that could have been a cooler period for the planet. And you know what? It was. If I'm going to skip down over to, let's take a look at this, okay? I'll go back. But anyway, I want to show you this is the time of the Maunder minimum, all right? It was a definite cooling off. We call it the Little Ice Age. We have historical evidence showing clearly that, for example, alpine glaciers were advancing down slopes in the Alps in Europe, and villages had to be abandoned. Glaciers were coming down and taking out villages. There's a recorded written history of this. So it was definitely a cooler period that does coincide with the Maunder minimum. Remember, a minimum of sunspots. So there's definitely a correlation between a minimum number of sunspots being recorded and a cooling off on the planet. Is that a cause and effect? Can't say. All we can say is that two things occurred together. It certainly suggests that there's a cause and effect, but we can't prove that. All right. But anyway, that's an interesting event. So let's go back to where we were here. Solar variability. All right. All right, number 4, orbital variability. Now, Milankovitch was a Russian scientist who, over 100 years ago, came up with this idea. He had figured out certain Earth-Sun geometry. In other words, A here, our orbit around the sun is not circular, it's elliptical, and that ellipse changes. So in other words, sometimes the Earth here is going to be further away from the sun, sometimes closer. Then that happens over a 100,000-year cycle. Changes in the Earth's tilt. Okay, in other words, right now we're tilted over at 23.5 degrees. However, that tilt changes over a 41,100 year cycle. Milankovitch had figured that out. And then changes in axial precession. What that means is Earth is spinning around, right? But it also wobbles back and forth. Imagine yourself spinning a top. Okay, it's spinning very fast, but slowly you can watch it wobble on its axis. So our planet does that as well. So when you combine all these three cycles, what Milankovitch suggested was that every 100,000 years, we should go into a cooling period. Now, his hypothesis was rejected until we were able to uncover Antarctic ice core evidence. All right, what you're looking at here is a chart that's taking a look at the amount of carbon dioxide and the temperature and the methane of air bubbles that we've retrieved out of an ice core drilled to the bottom of the Antarctic. Now, if you look along the bottom, you can see this 0 is present. And the Antarctic ice core goes a little over 400,000 years. So in other words, the ice at the bottom of the Antarctic is going to be a little over 400,000 years old. Now we are able to discern each individual year that snow fell and turned into ice in this ice core. Because remember, Antarctic is a glacier. It's all a result of snow falling, compacting, turning to ice over the years. Now, every year that snow falls, it's going to capture tiny little bubbles of the atmosphere and preserve them in that particular year in the ice core. We are able to extract those bubbles out in the lab and discern the amount of carbon dioxide, the temperature, and the temperature is based on the ratio between oxygen 18 and oxygen 16. It's very simple to do. And we've recreated this chart here, and look what it shows. It shows a cooling off period of about every 100,000 years. So this does prove the Milankovitch theories. This is what Milankovitch had thought was going to happen. So we see evidence in the Antarctic ice cores that we do cool off every 100,000 years. Okay, so that's going to be based on variations in the Earth-Sun geometry. All right, I wanted to show you this end of the last ice age. So the beginning, the Holocene begins about right here. Notice, we're coming out of the ice age here 18,000 years ago, but look at the variability. Yeah, sure, it's warming up, but then we get cooling off, a little warming up. A lot of variability. This is 10,000 years ago. But really, the climate did begin to warm up in earnest 10,000 years ago. All right, so we can see that. Now we can see also about 5,000 years ago, referred to as the Holocene maximum. The Holocene maximum was a time 5,000 years ago when it was warmer than today. Here we are today. All right. So again, I just want to put this in here to show you all the variability in the relatively recent geologic past that we've had. Again, this can't have anything to do with human intervention. All right. All right, finally, though, let's get to human activity. Now, I've put in quotes the enhanced greenhouse effect here. Let's think first of just the greenhouse effect. Our atmosphere has a natural greenhouse effect, okay? The gases of carbon dioxide, CO2, methane, CH4, and water vapor, H2O gas. Those are all greenhouse gases. What that means is those gases are very good at absorbing long wave radiation that's emitted from the surface of the planet. Now, put that word enhanced in front of it. It means we are adding greenhouse gases to the atmosphere and therefore enhancing it. That's what that term means. All right, let's take a look at that. So since the beginning of the Industrial Revolution, we can see that CO2, carbon dioxide, has increased from approximately 280 parts per million to 400 parts per million. Now, how do we know this? Well, on the summit of Mauna Loa, which is a volcano on the island of Hawaii, we have an atmospheric research station. And we've been measuring atmospheric chemistry for over 50 years on the summit. So over that 50 to 60 year period, this is what we've seen. We've seen this increase from 280 to 400 parts per million. And we believe most of that, if not all of that, is a result of the burning of fossil fuels, oil, natural gas, and coal particularly, that put out a lot of carbon dioxide. We can calculate the amount of carbon dioxide we put out around the world by just figuring out how much coal we burn, how much natural gas we burn, how much oil and fuel that we burn. So, okay. If we've made a 40% increase in carbon dioxide, doesn't it stand to reason then, if we have more carbon dioxide in the atmosphere, it's absorbing more long wave radiation and heating up the atmosphere? That's the hypothesis behind that. Now, if we go down to the number 2 here, CH4 is methane. We've seen a very large increase in methane to 1,800 parts per million, a 250% increase since we've been measuring this. And this is interesting to me because one molecule of methane is approximately 20 times more powerful at absorbing long wave radiation than carbon dioxide is. Yet you rarely hear about methane. To me, methane is a much more powerful greenhouse gas that we're emitting by burning fossil fuels, and there's other reasons that methane gets emitted. By cutting down forests and leaving the foliage to rot away, it releases methane. As the Arctic permafrost is melting because climate's warming rapidly in the Arctic, as the permafrost melts, all of that frozen organic material that's in the ice is now rotting and releasing methane. So we're seeing a big release of methane right now. And I think that's one we should be more concerned about, honestly, than carbon dioxide. But we don't seem to hear about it. And then finally, I've got one type of nitrogen oxide in here. That's from burning fossil fuels. We've seen a modest increase in that, but that is also a greenhouse gas. Okay, we already looked at that. So actually one more bit though to look at this. I already showed you this for the Little Ice Age here. But if we come into recent history now, coming up to modern day, we do see an increase in the temperature. So there are many ways we look at this. Okay, how do we know, the temperature's increasing? Well, obviously, first of all, we have thermometers. We call that the instrumental record. If we look at thermometers around the world, we see, recording the temperatures, we see an increase. Not everywhere. And here's the other issue you got to keep in mind. When we say the planet's warming, it's not warming everywhere on the planet. I mean, there are huge disparities of climate change in the planet. Like if we start with the northern part, the Arctic, that's warming up faster than any other location on the planet by far, okay? You're looking at about a 6 to 7 to 8 degree temperature in Fahrenheit rise in the last 40 years. That's significant, okay, on average. But when you go down, you can go down to the Antarctic. Let's go down to the South Pole. Our instrumental records demonstrate down there that the climate's actually cooling off. All right. Other places are cooling. For example, if you look at the southeastern part of the United States, across the Gulf Coast, Mississippi, Georgia, those states, they're cooling off. Okay, there's another location cooling off up around Iceland. Okay, that's cooling off. But if you take things as a whole and average it out globally, the average global temperature is rising, okay, if you average it all out. Like I say, though, some places are cooling, but most places are warming. There's certainly evidence of that warming in the United States. If you take a look, Glacier National Park, Montana, there's glaciers there. This is the Grinnell Glacier, 1938. I mean, you look at it in 2006, it's virtually gone. All right, so look at all this ice. Look at the ice sheet here, just a lake now. All right, I've done a lot of hiking and climbing in Glacier National Park over the last 40, 50 years, and I can tell you that I myself have seen the glaciers receding very rapidly up there. So, I mean, that's got to be a reflection of global warming, or at least warming in that part of the world. All right, so potential impacts of global climate change. I want to focus here on the Arctic, okay, the Arctic environment. Now, this first dash, I've got this Arctic ice likely to trigger ice albedo feedback. Okay, what do I mean by that? All right, now the way the ice works in the Arctic, okay, is that in the wintertime, that ocean completely freezes over. It's completely iced over, that entire ocean, okay? But as spring and summer comes on, the ice starts melting around the edges, all right? Now, if you think about that, when it's completely iced over and there's white snow on top of it, it's got a very high albedo. Right? In other words, you're getting a lot of reflection of shortwave solar radiation. However, when you start melting that ice down and allowing ocean surface water to be exposed to sunlight, ocean water has a very low albedo, which means it's absorbing a lot of shortwave solar radiation, therefore heating the water up. If you heat the water up, you're going to melt more ice, exposing more surface water to shortwave solar radiation, and you're going to start speeding up this whole this whole notion of melting the ice. That's what we call positive feedback. Okay, they call it ice albedo feedback. It's a form of positive feedback. In other words, it accelerates the melting of the sea ice. All right. Now, if you take a look at this graphic over here, what you see is from about, late 1970s to just about the present time. This is going to be the average monthly Arctic sea ice extent in September. Now, why September? Because this is the month we take a snapshot of how much ice cover there is, because September is usually the month when we have the least amount of ice left. We've reached our maximum summer melt. So we've got a snapshot of this going back to 1979. Every year we've done that. Well, take a look at that. Since 1979, the average monthly Arctic sea ice extent. You can see that it is reducing, okay? The red is the line of best fit. We're seeing a steady decline in the Arctic sea ice as of September. So it's really happening, okay? Now, some interesting impacts, potential impacts of less Arctic sea ice. And we're seeing this dramatically already. As we reduce the amount of Arctic sea ice in the Arctic, we are opening up major opportunities for shipping lanes. I'm not suggesting this is good or bad. I'm just saying this is what's happening. You can significantly reduce the amount of time travel, say in a ship from Europe to Asia, by going through the Arctic, okay? Not to mention Arctic resources. Now, there is an Arctic Council that consists of all of the countries that border the Arctic. This is going to be countries, United States, Canada, Scandinavian countries, Denmark, because they own Greenland, and Russia. There's a council that they're all members of. They're trying to decide how to deal with the Arctic as that sea ice opens up, because there's going to be opportunities, not just for transportation. There's going to be opportunities for resource extraction. How is that going to work? So anyway, that's coming, and it's coming in the near future. All right, in terms of, how humans are affecting the climate, there's a group called the Intergovernmental Panel on Climate Change, or the IPCC. Now, what this is a group appointed by the United Nations of many climatologists around the world, many participating climatologists. What they do is they get together every few years, and they come up with, basically a state of the climate report. You could call it that. Well, here's just a couple of highlights I put in here from the latest IPCC report. First bullet: warming of the climate is unequivocal. Okay, that means it's happening. There's no doubt about it. Overall, the climate is warming. If you're going to deny that, well, you're not looking at the evidence. Okay, and at this point, let me inject something here. It's really important to separate out two questions regarding climate change. Okay, and the first question is the climate warming? I don't care why. Number one, is the climate warming? Yes. Okay, now, number two, why is the climate warming? Do not mix those two up, okay? And that's where, the media and a lot of bad information out there is mixing those two things up. People who don't think humans are causing climate change are saying global warming is a hoax or whatever. Well, the climate is warming. The very first slide I showed you in here shows you how the climate has changed significantly throughout Earth's history. It's no big deal the climate's changing. It's changing. It always has. So climate is warming. Okay, that is unequivocal. Now, we can argue about why, but let's just continue on here. Second bullet down. Sea level rise we can measure at about 3 millimeters a year. Now, if you're not used to the metric system, 3 millimeters is about 1/8 of an inch. So that's the kind of rise we're seeing on the east coast of the United States. All right. So now there are a couple of reasons why the sea level could be rising, but according to the IPCC, they're suggesting most of this rise is due to two things. Okay. Number one, if the climate's warming, we're seeing a lot of melt, particularly off the Greenland ice sheet. And they think that's one of the reasons we're seeing sea level rise. But also, as the temperature of the ocean warms, it expands thermally. It's called thermal expansion. Think of a liquid in glass thermometer. When the temperature goes up, it doesn't matter what kind of liquid you got in there, mercury, alcohol, you can use water if you want. Any kind of liquid inside that thermometer, when the temperature increases, what happens? That liquid expands and it moves up in the tube. And when the temperature goes down, gets colder, it shrinks. So if we're going to warm water up, we're going to expand it. So both of those reasons are about equal in terms of why we see the sea level rising. Okay, now there could be another reason though why sea level is rising, all right? Could be land is subsiding, and we're seeing that in places. For example, there is some subsidence going on along the east coast of the United States. There are other places that are doing that. So we got to be careful when we see along a coastline sea level rising. Is that all due to an increase in the amount of water in the ocean from thermal expansion and glacier melt, or is it a result of the land subsiding? Okay, that gets kind of complicated. But nevertheless, we do see a sea level rise of about 1/8 of an inch a year along the east coast of the U.S. All right, third bullet. IPCC states that most of the observed increase in globally average temperatures since the mid-20th century is very likely due to the observed increase in anthropogenic greenhouse gas concentrations. All right, let's talk about that. You notice that very likely is italicized. That means we're not positive, all right? It's a little wiggle word, very likely. Could be they're wrong, all right? They don't think they are, but they could be wrong, all right? And the other term, anthropogenic, that just means human-made. So in other words, by we humans burning fossil fuels and releasing carbon dioxide, methane, nitrogen oxide, we think that's the reason the climate is warming right now, okay? Okay, so that, to me, there are other groups. This is the largest group of climatologists that get together and take a look at it. So this is the science. I mean, you can bring in other stuff if you want, but this is the science of climate change right here. All right, and if you want to get into some more details regarding how they approach this, you can take a look at this. Anthropogenic versus natural forcing. Forcing just means change. If you look along here at the left, anthropogenic, what we're doing, what's happening naturally. I don't really need to go through this very much, but when you see red, that's going to be increasing the temperature, forcing the temperature up. But there are other things at work that are going to be looking at cooling things down. Total aerosol, for example, and an increase in clouds are working to cool things off, all right? Now, the aerosols are coming from burning of fossil fuels. So the burning of fossil fuels, it's interesting, has two effects on forcing a climate or warming it or cooling it. On the one hand, by releasing carbon dioxide that absorbs long wave radiation, that's going to work to warm the climate. Here's your methane working to warm the climate. But when you get down to the aerosols, we know that reflects shortwave solar radiation, so it's actually working to cool things off. So if we weren't releasing all these aerosols, probably be warming things up even more when we get down here to total net anthropogenic here. So total net anthropogenic, you can see we're looking at about an increase of about 1.5 watts per meter squared. Remember what I said earlier in this lecture, that the solar constant's 1,366 watts per meter squared of shortwave solar radiation that arrives at the top of the atmosphere. We are increasing that, we believe, by about 1.5 watts per meter squared. Okay. All right, so, really in kind of summary of all this, in terms of the science of it, it looks like if we take a look at the Milankovitch cycles, remember the cooling every 100,000 years, that over the next 10 to 20,000 years, the Milankovitch cycles favor a return to a cooler period or ice age conditions, all right? The second bullet down, rising concentrations of greenhouse gases are likely to cause global warming to continue through the century. I mean, are we going to reduce the amount of greenhouse gases we're releasing? Doesn't look like it, because obviously the United States is not the only player when we talk about global greenhouse emissions. We've got big countries like China in particular, India is coming on, that are developing, and they're probably going to start releasing more and more of this stuff. So let's just, instead of talking about this last one, let me just go to my last slide here. You can say what you want about computer models, the old phrase, garbage in, garbage out, but let's just take a look at them. Here's several computer models that are trying to model the future. You can see, if you want to get, you look these up in more detail if you want to, but let's look at this. So if you look about where we are right now, 2016, the computer models are showing that either that's going to be the low end, this is going to be the high end of what we can expect in temperature change by the year 2100. So in other words, the lowest end of this shows an increase of 1 degree Celsius, which is 1.8 degrees Fahrenheit, 1 degree Celsius increase of temperature by the year 2100. If we go up and take the worst case scenario, we're looking at almost 6 degrees or 5.5 degrees Celsius temperature increase by the year 2100. But like I say, models are only as good as the information we feed into them, all right? But nevertheless, these are what the model's saying. All right, so this is it. This is my last lecture, and I just wanted to leave you with the latest science on global climate change. All right, goodbye.